Hello everyone, welcome to video lecture on transport phenomena. Myself Khushbu Shah, Assistant Professor in Chemical Engineering Department of LG Institute of Engineering and Technology. In our previous session of transport phenomena, we have started a new derivation for the equation to derive of momentum flux distribution and velocity distribution for flow through circular tube. In that session, we have already covered first part of our derivation, which is the equation for momentum flux distribution. In today's session, we will see the second part of the same derivation, which is to derive velocity distribution. So let's start that. For flow through circular tube, we have already reached to this equation number 1 in our previous session, which is momentum flux equation. So momentum flux equation distribution is tau rz is equals to P0 minus PL divided by 2L into R. This is my equation for momentum flux distribution derivation. Now to derive velocity distribution, we have to use this equation. What we will do? We will just put the value of tau rz. What is the value of tau rz? Which we will get from the Newton's law of viscosity. So we will put the value of Newton's law of viscosity, which is tau rz is equals to minus mu curly Vz by curly R. That we will put in this tau rz equation. So from Newton's law of viscosity, tau rz is equals to minus mu dVz by dr, which is my equation number 2. Now we have to put this value of equation number 2 in equation number 1 and just rearranging the equation. What we will do? We will put the value of equation number 2 in equation number 1 and just rearranging the equation for velocity distribution. What will be my equation? dVz by dr is equals to minus P0 minus PL by 2 mu L whole outside R. Fine. We are just simplifying the equation by putting value of tau rz from equation 2 in equation 1 and just rearranging the equation for velocity distribution. So dVz by dr is equals to minus of P0 minus PL outside 2 R divided by 2 mu L. Now, what is the next way? We have to do the integration. Fine, because we want equation in the form of Vz. But here we have equation for dVz by dr as velocity is changing with respect to distance. So we have to do integration. So after integration, the equation becomes Vz is equals to minus P0 minus PL by 4 mu L into R square plus C2. Fine, C2 is the integration constant. So now equation for Vz having some constant value C2 will be Vz equal to minus P0 minus PL by 4 mu L into R square plus C2. Now we know for evaluating value of any constant we have to apply boundary condition. So the constant of integration evaluated by applying boundary condition, and now here the boundary condition will be at R equal to capital R Vz is 0. Just revise the figure or just revise the system which we have considered. What is our system for flow through circular tube? We have considered a cylinder pipe or tube, and in that we have considered a thin cylindrical shell having radius small r. But now I have to evaluate the constant, so I am applying boundary condition for the whole tube, and the radius of the whole tube will be capital R. That we have already considered when we have seen the figure. Fine. So here I am applying the boundary condition. At small r equals to capital R, my Vz will be 0. We know that the velocity at the surface of the tube will be 0 always, and as we are going away from the surface of the tube, the velocity will increase. So that's why here I am applying this boundary condition that at r equals to capital R, my Vz will be 0 or the velocity will be 0. So when I am applying this boundary condition r equals to r, Vz will be 0, you will get the value of C2 will be P0 minus PL capital R square divided by 4 mu L. You can see in this equation. Here the Vz 0, that means this term is 0. As this term is 0, what is C2? The remaining P0 term will go on this side. So my C2 value will be P0 minus PL into capital R square divided by 4 mu L. So this is value of C2. Now what we'll do? Putting this C2 value in equation of Vz, in equation number 3. You can see here, I am putting this C2 value in this equation number 3 to get the final equation for velocity distribution. Fine. So putting value of C2 in equation number 3, we get this form of equation. I have just put the value of C2 in equation number 3 and I am taking the common terms outside the equation, outside the bracket. So the Vz is equals to P0 minus PL into capital R square divided by 4 mu L into bracket 1 minus small r by capital R whole square. This whole term P0 minus PL into capital R square divided by 4 mu L I have taken outside, common. Fine. So that's why remaining term will be remain in the bracket, which is 1 minus small r by capital R whole square. This is my final equation of velocity distribution, or I can say this is my final equation of Vz. Fine. So this is the second part of our derivation of flow through circular tube, which is of velocity distribution. Fine. So if sometime the question, or I can say the example will be asked in the exam, in that the situation is given for the circular tube and it may be possible that it will be asked that calculate the velocity for this case for flow through circular tube. At that time you have to use this equation directly, which is the equation of velocity distribution. See here. This is the profile. This figure shows the velocity distribution profile as well as momentum flux distribution profile. See here. See. This profile, which you will see, it look like this parabolic profile. Fine. This parabolic profile shows the velocity distribution. Here, see this part of the sketch. This is the parabolic velocity distribution profile Vz of r. And see, bottom of this figure, it will shows like this. At the center, it will be 0 and like this. So this sketch shows the linear momentum flux distribution. Fine. So this figure shows the profile for parabolic velocity distribution and linear momentum flux distribution. So from this profile you can say that the momentum flux changes linearly and velocity changes parabolically. That this sketch shows. Fine. So this is all about momentum flux distribution and velocity distribution. Now if we will know the velocity distribution for any system, we can calculate some other quantities from that. So let's see that what are that quantities. As once we get velocity distribution, a number of quantities can be calculated. And what are that quantities? First quantity is maximum velocity. We all know that the maximum velocity Vz max, which is at r equals to 0. So the maximum velocity is that velocity at which radius will be 0. So in our Vz equation, which is our velocity distribution equation, in that put small r is equals to 0. So when you will put small r equals to 0, your equation will be for Vz max, and it will be Vz max is equals to P0 minus PL into capital R square divided by 4 mu L. Fine. We have just putting small r equals to 0 in our velocity distribution equation, in our Vz equation to get value of Vz max. So when you put r equals to 0, small r equals to 0, be specific. At that time, your maximum velocity, that is Vz max, is equals to P0 minus PL into capital R square divided by 4 mu L. So this is the equation to calculate maximum velocity in flow through circular tube. Fine. Next quantity is the average velocity. How to calculate average velocity? The average velocity is obtained by dividing total volumetric flow rate to cross-sectional area. We know that velocity is volumetric flow rate divided by area. But for average velocity, we consider the volumetric flow rate divided by cross-section area by this equation. See, average velocity denoted by this symbol, integration 0 to 2 pi integration 0 to capital R Vz R dr into d theta. Whole divided by, that means this above term, this term will describe the volumetric flow rate. And in the bottom, integration 0 to 2 pi integration 0 to capital R dr d theta. So this denominator term will describe the cross section area. So the above term is the volumetric flow rate, below term will shows the cross section area. So dividing volumetric flow rate by cross section area, we will get the velocity. So when you will solve this integration, you will reach to the form P0 minus PL into capital R square divided by 8 mu L, and which is, you will see the equation of maximum velocity, it is what? P0 minus PL capital R square divided by 4 mu L, and average velocity is P0 minus PL capital R square divided by 8 mu L. So I can say that average velocity is half of the maximum velocity. Fine. So average velocity is 1/2 of the Vz max. So this is the second term. Now let's see the next term, which is the mass flow rate. Fine. Mass flow rate is obtained, which is the product of cross section area, density and average velocity. So we have to just do the multiplication of area, density and average velocity. We have all the equation. We have equation for area, we have density rho, and we have equation for average velocity. Here we have this average velocity equation, right? So just doing the multiplication of all three, area, density and average velocity, you will reach to this equation. We describe mass flow rate by the symbol small w. So small w is equals to pi P0 minus PL capital R raised to 4 into rho divided by 8 mu L. So the mass flow rate equation will be this, which is obtained by multiplying these three quantities, area, density and average velocity. When you multiply these three quantities, you will reach to this equation of mass flow rate. And the last quantity, which is the force per unit area. See, the Z component of force Fz of the fluid on the weighted surface of the pipe is just the shear stress. I am repeating again, the force in Z component, which is Fz of the fluid on the weighted surface of the circular tube, is just the shear stress, which is denoted by tau Rz, and it is integrated over the weighted area to get force. So what we have to do? Fz is equals to 2 pi capital RL. Why I have written capital R? Because now I am considering force for the whole circular tube, not for the thin cell. Fine. So Fz is equals to 2 pi capital RL minus mu dVz by dr. This is the value of tau Rz. Fine. So minus mu dVz by dr at r equals to capital R. So when you open this bracket, you will get this, and when you put the value of mu dVz by dr, we have the value of mu dVz by dr when we are deriving the equation. Fine. And when you put the value of mu dVz by dr and simplifying it, you will get the equation as pi r square P0 minus PL plus pi r square L rho g. So this is the final equation to calculate force per unit area in case of the flow through circular tube. So by this way we can calculate these quantities. Which are the quantities which we have calculated? Force per unit area, mass flow rate, average velocity and maximum velocity. So when we have the equation of Vz, the equation of velocity distribution, we can easily calculate these quantities. Fine. So we have covered the derivation of flow through circular tube, second part which is velocity distribution, and how we can calculate the other quantities from the velocity distribution, that we have covered in this lecture. I hope the session is clear to all. Thank you.